Objective 2.7, finding rational zeros. So starting with a little bit of vocabulary, it says that according to the rational zero theorem, if f of x equals a sub n x to the nth plus, so basically f of x is a polynomial, has integer coefficients, so that's important, it only works if we have integer coefficients, then every rational zero of f has the form p over q, where p has to be a factor from the constant term, a sub 0, and q has to be a factor from the leading coefficient, a sub n. So if you have a polynomial, excuse me, and you can find the zeros of that polynomial, they always have to fit this criteria. P over Q, where P is a factor from the constant and Q is a factor from the leading coefficient. Okay, that's going to be very helpful for us in big type of zero, a specific type of number. We've got to make sure that our answers fit this type. Okay, so we're actually going to start by listing the possible rational zeros. So in the last lesson, I told you, here's a zero that we already know is going to work. Use that to find the other zeros or the other factors. But when you have this problem, you are not being told where to start. You have to figure out what's going to be a zero that's going to work. So with no guidance, that's an almost impossible task. Where would you start? What numbers should you try? What zeros might possibly work so that you're not working on this for hours on end? So from our vocabulary, we're going to use the fact that if there are rational zeros, they have to fit that P over Q form. And we're going to make a list of all the possible rational zeros by using that form. So we identify the leading coefficient, which is the 3, and the constant term, which is the 6. And then we're going to set up P over Q, which the vocabulary definition said has to be factor of the constant term over the factor of the leading coefficient. So we're going to look at all of the factors of the constant. So for 6, which is the constant, we have factors of 1, 2, 3, and 6. Now notice in front of each number I have plus or minus, because it is possible that it could be a negative 2 times a negative 3 that got us positive 6. As well as it is possible that it could be positive 2 times positive 3 that got us 6. So we always want to list the factors with plus and minus in front of them. Now that gives us our numerator. In our denominator, we want to list all of the factors of our leading coefficient. So since that is 3, we would just have plus or minus 1 and plus or minus 3. Now, in order to set up the list of all of the possibilities for P over Q, we are literally going to take every combination of factor from the constant over factor from the leading coefficient. So you can see here that I can start out by taking 1 over 1, and that's right here. I can take 1 over 3, and that's right here. Then I move on to 2 over 1, so that's that. 2 over 3 is that one. 3 over 1, right there. 3 over 3 is that one. 6 over 1 is right there. And finally, 6 over 3 is that one. Okay, now we're going to take all of these combinations and we're going to simplify them. So 1 over 1 is 1. 1 over 3 is going to stay 1/3. 2 over 1 is 2. 2 over 3 is going to be 2/3. And then notice I get 3 over 1 is 3, but then I get 3 over 3. That simplifies to a 1, but I already have 1 in the list, so I don't need to list it again. Then I have 6 over 1, which gives me 6, and then finally 6 over 3, which simplifies to 2, and again 2 is already on the list, so I do not need to list it again. So what this tells me then is that if there are any rational zeros for this polynomial, it's got to be something on this list. It does not mean everything on the list works. It just means that if there is a rational zero, it has to be one of these 2, 4, 6, 8, 10, 12 possibilities. And keep in mind, we do have 12 possibilities because there's the positive and the negative for each one of these numbers. Now that might still seem like a lot, but it's better than infinity. So these 12 possible rational zeros now give us a place to start. These are the numbers we can start testing with synthetic division to see if any of them are going to work. Okay. All right, so here's our list. Let's start testing them. So I'm going to start by testing the 1. So you can see I have my coefficients there of 3, -4, -17, and 6. And when I test 1, I end up with a -12 out here in the remainder. So based on what we did last lesson, that -12 tells me that 1 is not a 0, and therefore x minus 1 would not be a factor. Okay, so I move on. I try something else. Maybe I could try a -1. So again, same coefficients, 3, -4, -17, and 6. But now I have -1. And as you can see, that still does not give me 0 as a factor, or excuse me, as a remainder. So I try +2. Well, that gives me -20. Still doesn't work. Maybe I try -2. And there I get my bingo, along with this silly little message. There we go. All right, so now I have something that works. Now I have that 0 right here for the remainder. So now that I have what I want, what do I do with that? Okay, so here's the result we got. Since the remainder for x equals -2 is 0, that tells me -2 is one of the zeros of the function, and it tells me x plus 2 is a factor of the function. I also know that the 3, -10, and 3 are giving me the coefficients on a polynomial with one less degree, which in this case would be quadratic. So I can rewrite using the 3, -10, and 3. I can write the other factor as 3x squared minus 10x plus 3. So at this point, I would call this 3x squared minus 10x plus 3 a reduced polynomial, meaning I started with a cubic polynomial, I divided one factor out, and this is the reduced polynomial that I get as a result. And so I can rewrite my original cubic polynomial now as two factors, x plus 2 times 3x squared minus 10x plus 3. Now, just like we were doing last lesson, I look at this quadratic and I try to decide if I can factor that even more. And in this case, the answer is yes. 3x squared minus 10x plus 3 can be factored into 3x minus 1 and x minus 3. So now I can identify my zeros by setting each factor equal to 0, and I get x equal to a -2, a 1/3, and a 3. And if you go back to that list of possible rational zeros that we started with, you'll notice that all three of these numbers are on that list. Okay, and all three of these are rational numbers because they can all be written as a fraction. And so we have answered the question and we have given the answer that it's looking for. All right, why don't you give one a try? Take the polynomial 2x cubed plus 2x squared minus 8x minus 8. Work through the same process that we just saw in example 1, where you find the list of possible rational zeros first, and then you start testing those to see what's going to work, and then take your reduced polynomial, which should be quadratic, and see if that can be factored any further to get your final answer for rational zeros of the function. Don't forget to answer the Zaption question to the right, and when you've finished, come back so you can check your answer. All right, so starting with the possible rational zeros, we're going to take the factors of -8 over the factors of 2, and all of the different combinations ultimately end up giving us plus or minus 1, plus or minus 1/2, plus or minus 2, plus or minus 4, and plus or minus 8. So when we start testing those, we find out that -1, -2, and +2 are all zeros that would work. So it just depends on which one of those you found first, and then the quadratic that you get will find the other two for you. And so from our factors, we can get our final answer of rational zeros, which is -1, -2, and 2. All right. Now, one of the things we need to understand, we throw a lot of these words around, the zero, the factor, the solution, the x-intercept, and it may seem like because we're using different words, we're talking about different things. And to some extent we are. But we also need to realize that all of these things are interconnected with each other. And so they're very, very similar, along with being slightly different. So this box is just helping us to bring all of those ideas together and point out their similarities and their interconnectedness. So it's basically saying if you have a polynomial function, that f of x as a polynomial function, then these statements are all equivalent, meaning they're all basically saying the same thing and yet saying it just a little bit differently. So a zero is a number that you can find for a function. So we say that k is a zero of the polynomial function f. It means if I put in k, whatever that value is, for x, I get 0 as an answer. But we don't actually start with an equation that says make this equal 0. We're just starting with a function and we are asked to find the zeros. Now if we skip down to solution, that's almost the same thing, except we say we want the solution of an equation. So we're already starting out saying a particular polynomial equals 0. And when we find the values that make that true, then we call that value a solution, Whereas with zeros, we're just looking at the function to start with and finding those values give us zeros. So very, very similar there. The piece in the middle, the factor, is what we can get from a zero. So once we know that we have this k value as a zero or as a solution, we can also then assume that x minus k would have to be a factor of the polynomial that we started with. Okay, and we've been seeing that as we've worked through the problems the last couple of lessons, that when we find a zero, we get a factor. If I know the factor, I can find the zeros. If I know how to factor, then I can solve equations when we're equal to zero. All interrelated. The additional piece here is the graphical part. And the graphing piece says that if k is a real number, then if I look at the graph of the polynomial, those k value zeros are also going to be the x-intercepts on our graph. And that's a really important connection to make too. So it's taking zeros, factors, and solutions, which are very algebraic, and it's giving us a graphical connection, which is that the zeros and the solutions are the same as the x-intercepts on our graph if those k values are real numbers. Okay, so as we use these words, zeros, factors, solutions, intercepts, just understand that they're all very much connected to each other, and what we're being asked for really isn't that different. And we'll continue to use these terms and to use the fact that these four statements are equivalent in our upcoming lessons. All right, so let's expand just a little bit. And now, instead of just finding rational zeros, let's find all real zeros. Now, the process is not any different. We're still going to start by finding the possible rational zeros because we know what we have to do to get those set up. So in this case, the factors of our constant are going to be the factors of 4, so 1, 2, and 4. Again with plus and minus in front of each one. And the factors of our leading coefficient will be and so all of the different combinations of that will give us plus or minus 1, plus or minus 1/3, plus or minus 2, plus or minus 2/3, plus or minus 4, and plus or minus 4/3. All right, so now using that list, we're going to start testing zeros. So maybe I start by testing x equals 1. That doesn't work. I get a -2 for a remainder. So maybe I'll try the -1 instead, and boom, that one works. So getting a remainder of 0 means -1 is going to be one of my zeros. And I get one step closer to finding all of the factors and all of the zeros, because I can now rewrite this as x plus 1 times the reduced polynomial, which is now 3x cubed minus 2x squared minus 6x plus 4. Now, at this point, in some of our other examples, we've looked at the reduced polynomial and tried to factor it more. But my reduced polynomial this time is a cubic. So just doing a flat-out factoring is not going to be easy yet. So what we do is we take the same list of possible rational zeros and we continue to test more zeros, but using the reduced polynomial. So we don't go back to the original. We use that reduced polynomial, that 3x cubed minus 2x squared minus 6x plus 4, and we use that to continue testing other values. And so I find out that 2/3 is another number from the list that will work. And so I now know that x plus 1 is a factor. I know that x minus 2/3 is a factor. And now my reduced polynomial, my result, tells me that I have 3x minus 6 as a factor. Now that 3x minus 6 is finally quadratic. So I should be able to set each of these equal to 0 now and solve for x. Since 3x squared minus 6 is not a full trinomial, I don't really need to factor this anymore. I could, or I can just use finding square roots. So you see here when I set x plus 1 equal to 0, I get x equal to negative 1. When I set x minus 2/3 equal to 0, I get x equal to 2/3. When I set 3x squared minus 6 equal to 0, I can add the 6, divide by 3, and then take the square root of both sides. Just remember, when you take that square root, you need plus or minus square root of 2 so that you get your 4 answers in total. And so those are my zeros: negative 1, 2/3, square root of 2, negative square root of 2. Now in this case, I can use these two zeros, the sorry, I can't really see that, the square root of 2 and the negative square root of 2. Those are okay if I'm looking for real zeros, along with my negative 1 and my 2/3. But what if this had been a problem back in the first example where we could only get rational zeros? Then I would have to exclude these two. If this is just a rational zero problem, I can only use these two. But as a real zero problem, I can use all 4. Because the square root numbers are real numbers. Okay, so make sure you're paying attention to the directions. Make sure you're paying attention to what they're asking for so that you're giving a proper answer. All right, it's your turn. Go through that same process of finding your possible rational zeros. Start testing those zeros to see what works. And when you finally get down to a reduced polynomial that is quadratic, then you can use quadratic means to finish the factoring and find your zeros. Make sure you answer the Zapstring question on the right and come back when you're ready to check things out. All right, so our possible rational zeros in this case are going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. When you test them in synthetic division, you find that negative 2 and positive 1 are numbers that work. And that should get you down to a quadratic of x squared minus 3 equals 0. So when you solve that one, you end up with additional zeros of square root of 3 and negative square root of 3. All right, so that does it for this lesson. You now have what you need to be able to complete the practice problems for Objective 2.7. If you have any questions on this, find the resources you need to answer your questions, either by going back in the video or asking your friends, asking teachers, sending me an email, whatever you need to do. Don't forget to check your completed practice with the answers posted on Canvas. And that will do it for today. Good luck with your problems. We'll see you next time.